Good evening, everybody. Let's wait for 2-3 minutes and then we'll start. Okay, so let's start. So in this week, the lectures are mainly on the electrical conduction of metals. Uh, so just briefly what have been taught. So the lectures probably start with classical theory of free electron gas in metals. So the idea is basically in metals there is certain ion core, let's say positive, basically, and then electrons are valence electron mainly are roaming around in the material. Okay, and these electrons uh, conducts electricity whenever we apply electric field. So if we apply electric field, then there is a force develops which will be minus E electric field, uh, proportional to, let's say. So if you apply electric field in x direction, let's say, then electrons will go in the opposite direction due to this extra negative sign of electric charge. Okay, and this and by current we mean flow of positive particles. So in this direction electrons will flow, this direction current will go. So that's the classical theory of free electron gas. There are many more things, but the broad idea is this. Okay, uh, so there are some success of this classical theory or so-called Drude model. So one of the success is Ohm's law, which says that I V equal to IR, one of the mathematical form for Ohm's law. So which says that voltage developed, voltage equal to electrical current into resistance. So what is resistance? Whenever electron will pass through this metallic system, so they will scatter with each other, right? So this electron suppose go this way, this electron also suppose go this way, and then they scatter with each other. And that somehow stops the flow or resists the flow, resists the flow, which creates a hindrance for conducting that electricity, which is manifested in terms of resistance. And current is basically what we are driving in the system, applying external voltage. So V, and this will be I, and the metallic system resistance will be R. So this is one of the success. And then number two will be Weidmann-Franz law. Okay, so this says that so in a metallic system conducts electricity whenever we apply current, or if we apply temperature gradient. Let's say this is temperature high, temperature low, so this is hot end and this is cold end. So they will also transfer the heat, right? This is usually what we observe also. So this conductivity, so how much conductor they are of electricity, if we, so electrical conductivity, if we denote by electrical conductivity by sigma, and kappa is the thermal conductivity. So conductivity is nothing but the inverse of resistivity, let's say. So resistance, sorry, so resistance is related to resistivity, let's say proportional to it measures that how much bad the metals are in terms of electrical conduction, and the inverse of this resistivity rho is the sigma conductivity. So if there is conductivity is high, then this is also a good conductor, right? So similarly, if thermal conductivity is high, then this the metal also transfers the heat very easily. And Weidmann-Franz law says that the ratio of sigma by kappa or k is constant for a metal. Okay, so these are two major successes of this classical theory of free electron gas. Now there are many more failures, like if we increase the temperature of a system. Let's say I have a system, metallic wire, and I am increasing the temperature. Okay, now and also simultaneously sending the current. Now if I somehow measure the resistance, then it is usually observed that the as we increase the temperature, resistance also increases. And just hand waving answer would be there are many electrons, there are many ion cores inside the system. As you increase the temperature, the electrons kinetic energy gets increased. Kinetic energy. So electrons moves more randomly. Okay, and so there is frequent collision, and as a result resistance also increases. That's the typical observation. Hmm. But classical Drude theory says that resistance or resistivity should be proportional to root T. So as you increase the temperature, resistance also increases, but as a root T. But the in most of the experimental observation says that R is proportional to simply T, not root T. Okay, so this is one of the failure among many. And number two would be so number two is the heat capacity of metals. So Bude theory claimed that the heat capacity varies as probably heat capacity is actually constant. Heat capacity is defined by Cv equal to del U del T. U is the internal energy. Okay, and according to this is constant. Drude theory says that it is constant, but low temperature measurement of heat capacity in metals, again this is experimental observation as well as theoretically it can be proved. It's somewhat let's say constant at plus bt cube, I think most probably this is right. So this fails. Drude theory fails. There are many other failure as well. So the main problem is the electrons can't be treated as classical particle inside metals. Of course, few things they behave as a classical particles, not purely classical but somewhat classical. That's why Ohm's law is still sort of okay. Weidmann's law is also okay, but there are exception. But that's a different thing. Uh, I mean, more involved thing. So the point is this: electrons cannot be treated as a purely classical particle. Also, all of this classical theory uh, ob- assumes that electrons in the system in metals obey obeys Maxwell-Boltzmann statistics. So it says MB statistics says at an energy E, let's say electronic energy is E. So at some temperature it will be the probability of E will be okay. So the probability of electron at an energy E will be proportional to e to the power minus beta and electronic energy basically E. And beta is related to the temperature, Kb is Kelvin constant, and T is the absolute temperature. Okay. So this is also an assumption of classical theory of electrons, but electrons are actually fermions. You people will know this later about all these complicated, not complicated, but more subtle things. So electrons are fermions. So they actually follow Fermi-Dirac distribution function. Also, they follow Pauli exclusion principle. Okay, and what does this Pauli exclusion principle mean? So if I have a state at so if I have an electron at an energy E, let's say, and the electron's spin is up, okay, so then at the same state there cannot be another up electron with the same energy, okay. There can be down electron, because down electron is different from up electron. So that's what the Pauli exclusion simply says in simple terms. And what does Fermi-Dirac distribution say? So the again the probability of having an electron at an energy E is 1 by 1 plus e to the power beta epsilon, or let's say E minus mu. Mu is the chemical potential of the system. Okay. So yeah, so based on this Fermi-Dirac distribution and Pauli exclusion principle and other things, there is a new people in the field, Sommerfeld theory. So when Drude theory failed, Sommerfeld came up with his own idea, and it is a quantum theory, which essentially treats electron as a quantum particle. And in quantum mechanics, we treat particle in terms of wave function. Okay, we explain the behavior of a particle in the wave function in terms of wave function. So there is a concept of de Broglie, D will be small, which says a particle can have wave nature as well as uh, particle nature, and the lambda, the wavelength of that particle, is inversely proportional to the momentum. Okay, this is mv, which is the basic, if we observe or if we think about it, it is actually makes sense, because the heavier system around us, like with ourselves, or most of the things, ball or laptop or anything, are not really behaving like wave, because their wavelength is so small, h by p, right? So, but for electrons, this is the case. The electron can have duality nature, and electron are treated as a quantum mechanically wave functions. So, based on these, there are many consequences of this, but maybe this problem, sir may have solved, that if we have an electron and inside this there is no potential, but outside this there is infinite potential. What this necessarily means is that if we talk about in terms of quantum mechanics and wave function, then there is wave function of this particle which cannot go outside. Okay, outside it cannot go. And let's say if the width of the well, potential well, infinite well, is a, then the energy of the particle will be uh, first of all, energy will be quantized. So there is no continuous energy. There is no. So there are well-defined theory, and everything can be connected. But I am just going over very rapidly, so you may not be able to connect from where quantization comes, why it comes. But there is a background theory for everything actually. Lot of all of the other people comes into the picture, from Einstein, Dirac, lot of people actually. Okay, so there is no continuous energy of electron in this case, and En is equal to h bar square by 2m. M is the electronic mass, and n pi by a square. So n is the quantum of energy, or the level index, energy level index, and it can be actually n can go from 1, 2, 3, 4, etc. Okay, and A is the width of the well. So okay, so there are much more other things as well, but there is a concept of also the density of states. Okay, so what this necessarily means is that these are energy. Now I choose an energy window En plus 1 minus En, let's say. Or if you think about more simply, classically, I have an energy window DE. So this is energy scale, let's say. This is E1, this is E2. I chosen this much energy scale or energy width. So E2 minus E1. Now density of states D of E necessarily says that how much particle is there in that energy window. So Dn is the number of particle present in this energy window and divided by this dE, right? So per unit energy, how many particles are there or electrons are there in energy window dE? That's the simple definition of density of states. Okay, so let's stop here and move to solving some problems. First problem is just from simple Fermi-Dirac distribution function. Okay, so the question is the probability that a state which is 0.2 eV above the Fermi level. Okay, Fermi energy is just the chemical potential in this expression. So this is chemical potential or Fermi energy. There is subtle difference, but let's not go there. Fermi level or Fermi energy. So so the state is at 0.2 electron volt above the Fermi energy level. Let's say denoted by in a metal atom at 700 Kelvin is given by this. So let's just try to find out. So this will be the formula we need to use. So beta is 1 by kbt. Kb is 1.38 into 10 to the power minus 23 SI unit, and T is of course given 700K. So need to find the probability, and this also actually gives probability of having an electron at an energy E. Okay. So try to find out and then I'll solve. Okay, let's solve the problem. So we need to find actually f of E, and given E minus mu equal to 0.2 eV, and this is given because the energy level is at 0.2 eV above the Fermi energy, right? That means the energy is greater than mu by 0.2 eV. So if we put all these informations, f of E will be 1 by 1 plus 0.2 into electronic charge, that will convert it to SI. Kb is 700 into this is total exponential power, and if we found this will be around 0.035, and the answer is needed in the percentage, so the percentage will be 0.035 into 100. The answer is 3.5%. So this is the probability. The 3.5% probability is there for the electron to stay at energy E, which is higher than 0.2 eV at of course 700 Kelvin. Okay, so the second problem. Okay, so the question is an N-type semiconductor. Don't need to know about this material. I mean, for solving this problem at least, has electron concentration 3 into 10 to the power 20 per meter cube. So, okay. Hello, am I audible? Can anyone confirm? একটু নোংরা জায়গা। Sorry guys, I just got disconnected. I'm audible, right? Can anyone confirm?
Yes, sir, audible.
Thank you. Okay, so So the electron concentration is given and drift velocity is also given. Also the electric field that has been applied. So let's say we have a material, we apply electric field, external electric field of this 200 volt per meter, and it has electron density, uh, 3 3 into 10 to the power 20 per meter cube, and the velocity with which the electrons moves in the material is 100 meter per second. Now we need to find the conductivity. Okay. So the current density in the system is actually related to sigma, the conductivity, and the electric field by this relation. Okay, this is current density, and this is electric field, obviously, conductivity. And this conductivity is given by NeVd. So N is the concentration, electron concentration in that material, E is the electronic charge, mod value of that basically, and Vd is the drift velocity. Okay, so everything we know, then we can find sigma equal to so N will be 3 into 10 to the power 20 to electronic charge, 1.6 into 10 to the power minus 19, and drift velocity will be 100 meter per second. Okay, so if we found this, this will be, this will probably be 20, okay, so I actually have to calculate. Don't have an answer for that. So this will be 148 and 10 to the power 2.
4,800, sir.
Right, right. Yes, I am. Okay. So next problem. So by the way, so the relation between resistivity and resistance is, so if R is the resistance, rho L by A. So let's say I have an electrical wire of this is the cross section A. If it is cylindrical, then if the radius is smaller, then A will be pi R square, and the length is L, capital L. Then the resistance of this cylindrical wire or the material will be R equal to rho L by A, where rho is the resistivity, which is actually inverse of the conductivity, just we calculated. Okay, so conductivity if we know, then resistivity just inverse it, and if we know the dimensions of the material, so this L and the cross section, then we can know the resistance of the system, and the voltage it generates, voltage V equal to I into R. So the current, So you guys know about Hall effect? It have matlab it had been taught or not? Anyone? Okay, so probably it has not been taught Hall effect. So just a simple problem. So white A. Okay.
Girls on girls. Other other subject.
Okay. So consider an infinite potential well just had talked about. So V equal to infinity outside and V equal to 0 inside. Okay, the white is given as A. Now what it says is that let's say this is n equal to 1 level and this is n equal to 2 level for electrons. So the 2 level electrons have B times, so let's say E2 electron at 2 level energy E2 is B times E1 electron having energy E1 at n equal to 1 level. So we need to find what is B. Okay, this is a simple problem. The formula that will be used in this case is En, the energy of nth level is h bar square by 2m n pi by width of that well square. Okay, so let's just try to find what the B is. So try to find out and then I will solve. So Nyan found the answer. Very easy actually. If you have
Sir,
found,
I
Is it
think
4, sir?
4.7.
right. Okay, so let me solve the problem. So E2 will be h bar square by 2m into 2 pi by a square. So 4 into pi by a square. Now obviously E1 will also be this one apart from this 4 factor because n equal to 1 for E1, right? So then b equal to 4. Okay. So so again En we know n pi by L, let's say L is the weight instead of A. Now we need to find out the density of states that we just talked about at energy E for this system. So if I formally write the question, then it will be like yeah, just density of states for the so find out this is the question. So try to find it out. So the by the way the formula will be dNdE. Okay, so this is a not numerical value problem. So let me solve it. Even if you solve, it will be difficult to put out the answer. So we need to find out dE, density of states at energy E, which is dN dE. dN is the number of electrons here at an energy window dE. Okay. Now in the quantum well, So n equal to 1, n equal to 2, n equal to 3, etc. So and Pauli or Fermi-Dirac both distribution function or Pauli exclusion principle says that at a time, let's say n equal to 1 level, there can be only one electron, but there can be another electron with, let's say this is spin up, this will be spin down. So there can be only two electrons at a single level. Okay, similarly here as well, spin down, spin up, spin down, but this cannot happen like spin up. This is not allowed. Okay, so that's why we will multiply this with 2 into dn de. So from where this 2 factor is coming out, this is spin factor. So in conventional cells, we will say that there is only one electron can occupy at a time due to Fermi-Dirac distribution function and that Pauli exclusion principle. But it also says that it cannot be at the same state. So spin up state and spin down state are not same for electrons. Okay, this is a distinguishable property. Sorry, indistinguishable, but state are not same. So this is spin factor basically, or spin degeneracy factor. So now we need to find dn de. So en we know this expression, so we'll just take derivative of de and dn. So what will be that? To n, right? Then d of e will be it will be inverse, 2 into one by n. So this is the answer, but we can actually do better, because if you see, I am writing this as a function of energy. So density of states, I am short writing DOS, density T for density of states. Okay, so DOS is a function of energy, but here nowhere you can find the expression E. Rather, this is n, the energy level index, and all other things. So we can just again use this En formula, h bar square by 2m n pi by L square. So if you convert it, just I need to put n value. So it will be E L square by pi square into 2m by h square. So 2 into 2m by h square L by pi square into 1 by n. So this will be pi square h square by 2m and E L square. Okay. Okay, sorry. So the overall thing will be under root. So if we found it, it will be just a simple algebra. It will come out to be 4L by h bar into m by 2e root. So this is the final answer. So the density of state at an energy E is given by this expression. Now you see that the fundamental things are there: electronic mass, the width of the well, and only the energy, right? This is very necessary. We will always express density of states in terms of energy. Okay, so next problem. So the problem that we discussed of the quantum well was 1D, right? So 1D means so this is, let's say, along x-axis, and the wide the box is also along the x-axis. The width was L or A, whatever, and V was infinity outside, V was 0 inside. Now similar extension can be made for the 3D and 2D as well, right? Because so let's have a 3D box. Uh, and again here also, let's say the width is A, all are same, and similar thing happens here. Inside it V equal to 0, but outside, all the outside places V equal to infinity. Then the formula for this will be given by E. Now okay, so before that, let me remind that E where here was proportional to n square, right? This was for 1D. Now there will be another two different n for y-axis and z-axis. This was for x-axis. So this time energy will depend on three different level index, basically n2 and n3, and the formula will be given as again similar formula, pi square by L square, let's say, all are same, or a I have used, and this will be n1 square plus n2 square plus n3 square, just the sum of this all these things. So n1 corresponds to x-axis, let's say when I had only this 1D potential well. Then n2 comes from y-axis, 2D potential well, and then n3 z axis is also there. So this is for 3D case, okay, 3D quantum well of having width A. Okay, so related to that, I have a problem basically. That's why I told. Kinetic energy just means the energy that we have, because potential is anyway zero, already mentioned, right? So given mass of the proton is 1.67 into 10 to the power minus 27 kg, and also Planck's constant is also given. So this is H actually. Six 6.63 into 10 to the power minus 34 joule into second, and we are using H bar. H bar means H by 2 pi. Okay. So a proton is confined to a cubic box whose sides have length L or A, 10 to the power minus 12 meter given. What is the minimum kinetic energy? Minimum, and given MP and H bar. So again the formula is H bar square by 2 MP here, and pi square by A square. So formula is N1 square plus N2 square plus N3 square. Now we need to find the minimum. For that we need to know that which configuration will give minimum energy for N1, N2 and N3. Okay. So try to solve it and then sorry. So anyone found answer? SI unit or electron volume volt unit, whatever. Just think that which combination will give minimum energy. Again here as well N1, N2 and N3 all can be 1, 2, 3 and so on. Okay, it doesn't start from 0. So the combination is obviously 1, 1, 1. Okay, let me solve the problem. E minimum will be H bar square by 2m pi square by A square 1 square plus 1 square, right? So 3 into 6.63 into 10 to the power minus 34 by 2 pi h bar square, and then 1 by 2 into mass of proton 1.67 10 to the power minus 27 into pi square by L is 10 to the power minus 12 square joule. So if we calculate that, it will be around 9.9 into 10 to the power minus 17 joule. Okay, so this was the solution. So sixth question. Okay, so one question from the Hall effect, or let's skip that question actually. Okay, so the question is, for an ideal Fermi gas in 3 dimension, the electron velocity Vf at Fermi level is related to the electron concentration n by which of the following relations? N to the power half, n, 1/3 or 2/3. So no, D is not the answer. Uh, yes, D is not the correct answer. So I'll solve it. Yeah, yeah, C is the answer. Okay, so let's other. Okay, so solve it actually. So for a 3D system, the Fermi energy expression can be derived, but I'm not deriving here. So h square by 2m 3 pi square n to the power 2/3. Okay, n is the concentration. Now, now we need to find Vf, right? So Vf is what? Velocity when the electrons are at the Fermi energy or the Fermi level. So Ef is also the energy at the Fermi level. Energy at the now if Vf is the Fermi energy, then we can also say that energy will be half m Vf square at the Fermi energy, right? So just equate these two equation equal to, so then Vf will be proportional to n to the power 1/3, not 2/3, right? So C is the correct answer. Okay, so another related problem, very easy. So this is actually it. So the question is, if the number density of a free electron gas in 3D, again 3D, is increased 8 times, then what will be, how much the Fermi temperature will increase? So factor of 4 or decrease, whatever. So Try to find it out. So anyone found the answer? C is increased by a factor of 8. Not really.
Once you can explain, sir.
Yeah, I'll explain. Okay, so let me solve the problem. So Fermi energy for 3D again, h bar square by 2m 2/3, right? Now let's say what is given, n goes to concentration increased 8 times, 8n. So if we now represent Fermi energy by EF dash, then it will be h bar square by 2m 3 pi square into 8n to the power 2/3, right? Now we need to find it how much Fermi temperature will increase. So in case of kinetic energy, or let's say velocity, we applied this logic ki electron will have energy like this, half mv square, right? Purely kinetic energy, which equal to EF. Now we need to write the energy in terms of temperature. This is not temperature dependent, so this is easily written as Fermi temperature, kBTF. This is the temperature scale of Fermi energy. Okay, so EF equal to kBTF. kB is the Boltzmann constant. So now if we, let's say, kBTF dash this time, or it was earlier kBTF. So this part and this part, apart from 8 to the power 2 by 3, it is actually EF equal to kB TF prime. So 8 to the power 2 by 3 equal to kB TF equal to kB TF prime. So TF prime will be 8 to the power 2 by 3 times TF, and 8 to the power 2 by 3 is basically 4 TF. So the Fermi temperature will rise by 4 times. Okay, so increase by 4 times, that means option A. Okay. Another related problem. So the question is the radius of Fermi sphere for or of electrons in a monovalent metal with an FCC structure in whose volume of the unit cell A cube is this. So we need to find the radius. Okay, let's try. So these things has to keep in mind. Monovalent metal means the only one electron, and there is FCC structure, that means 4 atoms per unit cell. Monovalent basically means each atom contributes 1 electron in the conduction. Okay, so anyone found the answer? Okay, so we need to find the radius of Fermi sphere. Let's say radius is k, and this Fermi sphere or the Fermi surface, everything, all these concepts are in reciprocal space. Okay, not in real space. So that's why we are not denoting r but kf. So the radius, if we consider kf, then the energy ef will be h bar square kf square, basically free electrons energy. So what is the energy of free electron? P square by 2m, right? Kinetic energy. This is also P actually. P is h bar kf here. And we also know EF equal to, for 3 dimension, two by 3. Now the important point is we need to find n in order to find kf, right? If we equal this, then what we will get? Kf square equal to 3 pi square n to the power 2 by 3. This means kf equal to 3 pi square n to the power 1/3, right? So technically we got the expression, but we need n. So n is the electron concentration. That means that number of electrons per unit volume, right? So n equal to number of electron. Let's say n is the number of electrons by volume of the material. Now given that it has FCC structure, so in its unit cell, if we consider it A, then volume we know A cube, and it also has 4 atoms all in total in a unit cell. FCC has 4 atoms, and in electrical conduction each atom contributes only 1 electron. Why? Because this is given as monovalent. If it was bivalent, then it would have been 2. Okay, so this is because of monovalent. So number of electrons in an unit cell, if we consider, that is contributing to the conduction is just 4. So we got this 4 by V or a cube, whatever, right? So a cube. So then K becomes 3 pi square 4 by a cube to the power 1/3. So this is the radius of the Fermi surface. Okay. So radius is also related to the electron concentration. Okay, so next problem. So given the Fermi energy of gold is 5.54 eV, the number density of electrons we need to find. This is a very easy problem. Just solve it. So we just need to find what is N given EF, the formula. Okay, so let me solve it. Mm, So N will be just find it out. Oh, sorry. So this is overall square, right? So there will not be any square root here. So just need to put these values. Mass of electron is 9.11 into 10 to the power minus 31 kg, and then given EF is 5.54 eV, but we need to convert it into joule. So 1.6 into 10 to the power minus 19 by 2 pi square, and this is under 3 by 2 into 1 by 3 pi square. So if we find it out, n will be around 5.9 into 10 to the power 28, okay, per meter cube. So the answer is 5.9. So next problem. All are in SI unit. Okay, so current is given as 0.75 ampere, and the battery volt is 1.5, which is connected to a wire of length 5 meter and cross sectional area 2.5 into 10 to the power minus 7 meter square. We need to find the resistivity. So the formula that we already talked about, V equal to I R, and R is the resistivity into length of the wire by cross sectional area. So need to find what is rho. Try to find it out.
Sir, answer option A, yeah, sir.
Option A. Okay. So let's just find out. I also don't know the answer. So rho is VA by IL, right? So V is given 0.75 into
Sir, I value is
I value is 1.
current.
Sorry, this will be 1.5. Sorry, and this is 0.75. Uh, what happened? Okay, I need to reshare. 0.75 into length, right? 5 meter. So if the answer is coming 10 to the power minus 1.5 into 2.5, and okay, yeah, 1 is the correct. Option A is the correct answer, right?
Yes, sir.
So the next problem. So the next question is if the length of a wire doubles and cross sectional area gets decreased by a factor of 3, then what will be the new resistivity of the wire? So anyone? So R is rho L by A, and rho is intrinsic property of the material. So it will have different value for, let's say, silver will have some resistivity, copper will have some resistivity, and so on. And it's a property of material, not the material dimension. Okay, so if we increase the length, let's say this was the wire, if we increase the length and decrease that cross sectional area, then resistance will definitely change because of L and A. But the question is about resistivity. So resistivity remains same, okay, as long as you are not changing that material itself. So it doesn't change actually. So next question. So the next question will be on thermal conductivity. So we have a metal bar, let's say, and left end is maintained at higher temperature TH, right? This is also the origin of x-axis. Let's say this is x-axis origin, and there is a temperature gradient. So this is at higher temperature and this is at lower temperature. So temperature is decreasing basically along this direction at a uniform rate. So dt dx equal to minus gamma. Now need to find the thermal energy difference per electron between x minus v tau plus x plus and vx plus v tau. So let's say we have this is x minus v tau and this is x plus v tau. So what is the thermal energy difference between these 2 points, right? That we need to find. So let me solve the problem. Given the thermal gradient is dt dx equal to minus gamma. Now we can find, so this expression actually means that T is a function of position, right? That's why there is thermal gradient. There is no uniform temperature. At each point there is different temperature. So we can find that T of x equal to minus gamma x, right? Plus C, some integration constant. Now we need to find what is that integration constant, and for that we know one thing, that at x equal to 0 temperature is given Th, right? This is given. So if we put that in this expression, so T equal to at x equal to 0 Th minus gamma into 0 plus C. So then C is simply Th, right? Then T of function of position is minus gamma x plus Th. So this is the temperature profile of this bar, right? Now what is the thermal energy? So this is the temperature, okay, and we need to find the thermal energy, not the temperature. So the thermal energy per electron is given by, this is again classical theory, classical Maxwell-Boltzmann statistics following. Okay, so following Maxwell-Boltzmann stat. So this is thermal energy per electron, and in our case the temperature is position dependent. So this will be T of x, which is again 3 kb by 2 minus gamma x plus Th. Okay, so this is the thermal energy at some position, let's say x. We need to find, okay, so this is thermal energy per electron at position x, right? So we need to find thermal energy per electron at position x minus v tau minus E of x plus v tau. That was our primary goal, right? So thermal energy difference between these 2 points. So we simply put this x here, 3 kb by 2 in first case minus gamma into x minus v tau plus Th minus from this one minus of minus gamma x plus v tau plus Th. So if we simplify this, This will come 3 gamma V tau kb. So this is the delta E. So this is thermal energy difference per electron between these two position. Okay. Okay, so this was your last problem. So let me know if you understand this concept of this problem or not. Okay, so if there are no questions, then we'll end here. Okay, thank you for joining. I'm ending the meeting.